Hello, everyone. It's great to be here and great to see you here after 3 years since the last DevOps. My name is Patrycja Wegrzynowicz, and today I'm going to tell you about our multi-cloud deployment across AWS, GCP, and Azure with cluster mesh based on Kubernetes and Cilium. First, briefly about myself. I've been doing professional software development for over 20 years. Sometimes I feel like a dinosaur. My first love is software. However, last year I joined the dark side and became platform engineer for Form 3. I've been working on our multi-cloud connectivity and deployment. Nowadays, I'm lead engineer working on reliability and performance of our UK payments. What am I going to talk about today? First of all, why do we need multi-active, multi-cloud deployment at all? Then briefly about multi-cloud connectivity as the basis for our multi-active cluster mesh. Then very brief introduction to Kubernetes networking, and then Celium and its cluster mesh. Then I will show you a demo of working cluster mesh across 4 clusters and some summary and lessons learned from our work with Celium. Why do we need multi-cloud at all? So to answer this question, I need to tell you briefly about Form 3, the company I work for. So in 2 words, it's a financial cloud. So basically, it's a UK-based company, UK-based but remote first. So we are hiring developers across Europe and North and South America. So the main product is a payment platform for financial institution. Basically, we provide a REST API to multiple payment schemes like SWIFT, SEPA, FPS. We provide this integrated REST API to our clients, financial institutions, for them to make integration easier and quicker, so to save time and money. We are a very technology-focused company. So we are cloud-based. At the moment, our production systems work on AWS. Our new payment platform will be based on 3 clouds. Our architecture is based on microservices, written mostly in Go, but also in Java. And we treat infrastructure as code almost religiously. So we terraform everything what's possible. Challenges of payment processing. So basically, you can imagine how important it is to have reliable and durable payment processing when it comes to a financial institution. So outages and errors must be handled without any data loss. Plus, usually you have contractual obligations to maintain pretty high SLA numbers. Also, when you think about volumes, it might be pretty high as well for fast payment processing or any other, depending on throughput of our clients. So considering those requirements and thinking about maintenance in long term, it's very difficult to keep up to date with all those schema changes. So for banks or other financial institutions to provide ongoing maintenance and integration to multiple schemas is a huge burden. When we are thinking about cloud outages, is it okay to go multi-cloud? Is single cloud enough maybe? Let's take a look at 7 top cloud outages in last year. That's according to techgenics.com. So that's quite a lot, and it hit almost all major cloud providers. So any one of you have been hit by any of those? Raise your hands, please. Yeah, I see like almost half of you raising your hands. Yeah. So you know the problem. Myself, I was hit with my Discord server because besides of working at Forum Free, I also teach at University of Warsaw. And I used to have a Discord server for students and to do some sort of consultation with them. So our Discord server went down. So basically, you know why we need to go multi-cloud. Single cloud is not enough because an outage can happen any day. So requirements for our new payment platform, obviously we have all those very high requirements like high availability, resilience, scalability, performance, and last but not least, security. We've decided to use 3 major cloud providers, AWS, GCP, and Azure. And we've decided to use like cloud agnostic technologies, so Kubernetes with Celium as CNI, plus NATS and CockroachDB for streaming and storage technologies. So before we have an active cluster mesh, we need to connect 3 clouds together. And again, we had pretty high requirements for this multi-cloud connectivity. So luckily for us, we could focus on only one region because our first goal was London region and to prepare our platform to be available in this region. So considering this zero data loss, we had to have like a very good replication with NATS and CockroachDB. With good replication, it goes that we need low latency. So our latency should be under 5 milliseconds. Then we need a steady bandwidth. Obviously, we need security and preferably private connectivity. High availability and fault tolerance are a must. So in case of failure on any level, a link, a device, or point of presence of a cloud, we need to have like active setup to just switch to another link, device, or POP. So we research our connectivity options. So our 3 main connectivity options, or more like 2 connectivity options. So basically, we have VPN, virtual private network, across clouds. And that's a pretty good solution because all 3 cloud providers offer HA VPN solutions as out of the box. So basically, it's enough to configure. Considering our terraforming of code, that's also a plus because each of them, I mean, cloud providers, has their own Terraform provider, so we can Terraform our code, so that's pretty easy. The problem with VPN is that VPN is pretty unstable. Why? Because that's like encrypted to tunnel over public internet. So when something goes over public internet, you never know how it's routed and what problems can be on their way. So basically, even though you have like a good connectivity and good latency, from our tests, it was like around 8 to 12 milliseconds. So okay-ish. But still, we had like those anomalies when it skyrocketed to, for example, over 100 milliseconds. And moreover, we have also a kind of unpredictable routing. With financial data or confidential data, sometimes we have some regulations per country that our data can't leave a country or some region. So with VPN and public internet routing, you never know which route will be chosen. So basically, VPN was not our first choice, and even though we tested it and considered it at first. So we switched to direct connectivity. With direct connectivity, also each cloud provider offers their own solution for direct connectivity, namely Direct Connect, Interconnect, or Express Route. Basically, it's like your private link to a given data point of presence. With direct connectivity, we have two options. We can go to a company which offers like network as a service, and we can rent like virtual hosted connections or virtual network interfaces and a virtual router that connects all three connections. Or we can go to a physical data center, have physical routers, and connect our direct connections that way. With network as a service, that was really very promising solution. Why? Because, as I told you, we want to terraform everything. And basically, with network as a service, you don't have any burden to configure and maintain your own hardware and infrastructure in a data center. And we tested Megaport as one of cloud exchange provider companies. It worked pretty well. First of all, we could terraform. It worked out of the box. However, with hosted connections, it didn't work so smoothly with Terraform. It should be configured via a UI. The problem was that we want this redundancy, right? We want fault tolerance in case of failure on any level. So basically, Megaport provides HA connectivity option as well. However, in London region, the second route that time went through Frankfurt. So it meant to high latency for us, because latency was around 10 to 15 milliseconds. So after all, we decided on direct connectivity via data center. So we have our own physical router and third-party company which takes care of those configuration details. While we have only while we only touch cloud. So on high level, the overview is that we have redundant links. We have redundant data center presence. We have redundant links to each cloud. So basically, we have this high availability. The configuration is based on BGP protocol, so Border Gateway Protocol, where IP addresses are advertised and dynamically. It turned out that for each cloud, networking is configured quite differently, even though the general setup with redundant links or connections is the same. Once when you go to virtual private cloud or virtual network level, you have like different solutions with different capabilities. I think that AWS is one of the most offers more flexibility than the other clouds with its transit gateway setup and VPC attachments. However, you need to pay attention to network segmentation because default configuration might be unsecure, allowing to route with a single default route table on transit gateway level, allowing to route to all VPCs and all clouds without any control. Obviously, you can have like security groups, but from a high security point of view, it was not enough for us. We want to have like at least 2 control mechanisms in place for one area. So it's better to configure a network segmentation and different route tables per VPC as well. In case of GCP, they offer cloud router, however, it's not as easy to use as transit gateway. Why? Because you can't connect your virtual networks to cloud router directly. You need to have a separate virtual network representing transit network. Then you can have peering to transit network, but with peering you have the problem with network segmentation. So the solution to use on GCP side to provide network segmentation is to use HAVPN between GCP-based virtual networks. Similar problem you have with Azure, with Virtual One and Virtual Hub. You have like a full mesh. That's not what we want. At least when it comes to separation of concerns and defense in depth. So again, you need some other solutions like HAVPN inside Azure. On the other hand, with Azure, we had like a lot of problems with BGP configuration because it's the most limited clouds when it comes to configuring custom aggregation prefixes. Basically, it doesn't allow on custom prefixes. So basically, we can't announce like a single prefix in Azure. We need to announce specific prefixes for virtual networks. Anyway, and that's like a big topic for another talk as well. Let's move to Kubernetes networking and Cilium. With Kubernetes networking, you need to think about pod as like sort of virtual machines. Every pod gets its own unique cluster-wide IP address. All containers within a pod can communicate via localhost. And pods can communicate with all other pods on any other node without any NAT. So that's like basics and fundamentals of Kubernetes network model. Kubernetes with this pod network creates like a new layer of networking over host network. So that's why it's called like overlay network model. So a single pod or single container within a pod to communicate to a container in another node, it needs to go through virtual network interface, then through physical network interface on one host, and then almost the same way on the other host. Kubernetes networking is like sort of standardized. We have Cloud Native Computing Foundation and its framework called Container Network Interface, CNI. So the CNI specifies how to configure networking resources from containers. and container orchestrators. The responsibility includes network connectivity of containers, provisioning of IP addresses, maintaining connectivity across multiple hosts, and last but not least, garbage collection of resources. The important thing is that the CNI is plugin oriented, so we can have like different plugins implementing the same interface. Kubernetes supports CNI, and CNI plugin actually is required to implement Kubernetes network model. So in order to run Kubernetes on premises or in cloud, you always need a CNI plugin. We have different CNI plugins. We have like a bunch of generic ones, and I'm pretty sure that you know some of names like Calico, Flannel, Weave, and last but not least, Celium. As networking in clouds is very specific, each cloud provider for its managed Kubernetes offerings provides its own CNI. So we have AWS CNI, Google CNI, and Azure CNI. So let's move to Celium. Celium is a CNI plugin. What features does it offer? First of all, obviously, network connectivity. It must meet all those requirements and responsibilities of CNI plugin. But on top of that, it provides also security. Security via advanced network policies and encryption. And also offers cluster mesh, so it offers some sort of load balancing across many clusters. Celium operates in layer 3, 4, and also layer 7. That might be important for our network policies because we can specify specific policies for our applications, like for our HTTP, HTTPS traffic. And Celium advertises itself as lightning fast because it uses eBPF. That's like dynamic insertion of bytecode into Linux kernel. So Celium is able to do routing on kernel level, basically, instead of, for example, regular routing on IP table level. By the way, with IP tables, you have a problem because you have linear search in IP tables. What does it mean? It means that if you have like many rules configured in a single IP table or single chain, that may become very slow. So that load balancing, service discovery and load balancing I mentioned about refers to Celium cluster mesh, so we can connect multiple clusters in a single mesh, and we can have like a single global service, Kubernetes service, that it's load balance across many clusters. That's a very interesting feature. And it's very easy to implement because that's like a regular Kubernetes service with one extra annotation. With network policies, the interesting thing is that they are identity-based, so we don't need to take care of IP addresses. We can define them in terms of our application workload, for example, namespaces or something like that. Network policies are also multi-cluster and also can be applied to L7 traffic. That might be very interesting because we can filter out, for example, our traffic to public internet based on DNS names. Another interesting feature of Cilium is encryption. It provides encryption on a networking level via IPsec or WireGuard. However, it has a catch, but later about that one. And also we have pod IP routing, so we have pod-to-pod connectivity across multiple clouds. That's important because what Kubernetes guarantees is only pod-to-pod connectivity in a single cluster. So with Cilium cluster mesh, we have pod-to-pod connectivity across multiple clusters. This one may be configured via tunneling or direct routing. Tunneling basically encapsulates all network packets emitted by pods. So basically it means additional overhead. However, with tunneling, we have less requirements on the underlying network. What does it mean? It means that we only need to provide node-to-node connectivity to guarantee pod-to-pod connectivity across many clusters. Cilium supports two protocols, VXLAN in GNIF. We only tested VXLAN, it works well, so no problem here. With direct routing, basically all packets are routed directly to the underlying network. So in that way, the responsibility of the underlying network is to provide pod-to-pod connectivity. So it may require extra configuration in some cases on the routing networking level of our host network. However, when we are talking about clouds, it's simple. Because with clouds, at least AWS, GCP, Azure, we have pod-to-pod connectivity for free with default CNI plugins. What are the use cases for Cilium? As I told you, I think that the biggest advantage of Cilium is its global service feature. So basically we can have like transparent failover over multiple clusters. So when a service fails in one cluster, Cilium is responsible and guarantees to seamlessly fail over to another cluster. Also, interesting use case is a shared service. So we don't need to configure extra load balancer in front of a cluster anymore. We can use a global service and have the same service available across 3 clusters, even though implementation is present only in one cluster. Very similar use case with splitting stateful and stateless services. So basically, usually it's a good practice to have a separate stateful cluster because the operational characteristics of stateful and stateless clusters are different. So it's good to have them separate. So once we have a stateful cluster with data store service, it's kind of a shared service from the previous slide. How does Cilium organize its cluster mesh? So basically it's like a full graph. Each cluster is connected to each other cluster. In each cluster we have cluster mesh API server and Cilium agents running on each node. Cluster mesh API server is available as read-only source from other cluster and is writable only inside a given cluster. As I told you, each cluster must know all other clusters. So basically, a cluster endpoint is represented by a domain name and a set of certificates to connect. Important thing is that each cluster domain name must be resolvable to an IP address. It can be configured in two ways, via DNS or host aliases for Cilium agents. As you can see, you need to provide a Cilium cluster secret configuration for each cluster mesh API server. Basically, this includes data to connect to other clusters, so endpoint plus certificates. And here we have the first problem with configuration across three clouds. Because obviously cluster mesh API server should be configured as load balancer service type. So with load balancer service type, we have a problem with AWS. Because with host balancer service type plus host aliases. The simplest configuration is to use host aliases across three clouds because otherwise you need to configure multi-cloud DNS. So once you want to use host aliases, you need to know the IP addresses of your load balancers, your API, cluster mesh API servers. And we have a problem here with AWS. Why? Because load balancers in AWS are DNS based. So their IP addresses can change, basically, it means. So with Azure and GCP, load balancers are IP based. So once they are given an IP address, it's fixed. Another thing here is that in order to configure host aliases, you need to know those IP addresses beforehand. So you need like extra configuration to assign static IP addresses to your Kubernetes load balancer services beforehand. Okay, now it's demo time. Let's see Cilium cluster mesh in practice. As I told you, I have 4 clusters, 2 clusters in AWS and 2 clusters in GCP. The demo is Star Wars based. It's based on the demo provided by Isovalent, the company behind Celium. So basically, we have X-Wing deployment, we have Rebel base deployment. So let's board our X-Wing. We are at X-Wing, and let's try to hit our Rebel base. Our Rebel base is configured as a global service. So here we see that even though we are on cluster 1, that's our one cluster, we received a response from cluster 2. Let's try again. That was again cluster 2, but this time we received a response from cluster 1. So let's see how it's load balanced for more requests. And let's send like 1,000 requests to our Rebel base. Okay, and we see that there are also responses coming from GCP clusters as well. So that's global service in practice. But let's make it more complicated and let's see how failover works in practice. So now I want to scale our 4th cluster. So that's cluster in GCP, and I'm scaling it out to 0 replicas. So obviously it takes some time until Cilium cluster mesh notices a difference, until the pods goes down, until cluster mesh is refreshed. But we can see that we are now receiving only responses from 3 clusters. So let's do the same for another cluster. Scaling down the last GCP cluster. So now we have only EKS clusters in AWS. So we are seeing only responses from 2 clusters. And now it's the time for the last one. And now it should be only the first cluster, and form 3 rules the galaxy. Obviously, we are not that greedy. So let's go back and scale up other clusters. So with scaling up, it takes sometimes more time, but here we received a response from AWS cluster 2 pretty quickly. It depends on how quickly pods are spinned up and how quickly Cluster Mesh API server notices new active deployment of a given service. Okay, that was demo. Cilium Cluster Mesh in action. And now some lessons learned from our POC with Cilium Cluster Mesh. So first of all, as always, never underestimate the enemy. So even though our plan was clean and simple, the execution was pretty different, and we have a lot of ups and downs with configurations. Sometimes I felt like in a slapstick comedy, and I'm not a big fan of slapstick comedies, believe me. First of all, I was pretty new to Cilium, and when I started experimenting with Cilium. Cilium comes in 2 flavors. We have Cilium open source version, and we have Cilium Enterprise with support. Basically, both of them are very, very similar. However, usually Cilium OSS receives its patches much quicker. So sometimes that's kind of strange. Cilium CLI, that's like a client for Cilium that makes the configuration, it's supposed to make configuration easier. However, it's only available in Cilium OSS, and it's not recommended for Cilium Enterprise we are using. Anyway, I was experimenting with Cilium CLI, and I started with AWS, and it didn't work. Why? Because of hostname-based load balancer. So basically, Cilium CLI needs to know IP addresses of Cluster Mesh API servers beforehand to configure host aliases, and it couldn't discover that because those ones are not available for, we can't rely on them in case of AWS. There is a couple of tricks with Cilium, even though Cilium docs are pretty good. Again, rely on Cilium OSS because I was experimenting first with Cilium Enterprise, and unfortunately, Cilium Enterprise docs are far inferior to Cilium OSS docs. When you think about configuration new CNI for managed Kubernetes, you must consider how to disable an existing CNI and how to clean up your nodes, because Kubernetes needs CNI. With managed CNI, you have like a default CNI configured from the beginning. So you need to get rid of it and replace it with Cilium. CNIs basically work on networking level, and when you saw the slide with Kubernetes networking, you saw virtual network interfaces. So usually CNIs create extra virtual interfaces to manage this overlaid network. And once you delete one CNI, you need to clean up those network interfaces as well, plus bunch of other things as well. So sometimes it's not that tricky, it's not that simple, and it's pretty tricky to configure. Basically, it's good to, and actually that's in documentation, you need to change your node to no schedule until Cilium agents are ready, or you need to rescale your cluster, scale down to 0 and up in order to replace all old nodes with original CNI configured. There is a trick with Cilium operator role for EKS. As I told you, I started with Cilium Enterprise because I thought it could be like well documented. Unfortunately, that was not the case, and then I switched to OSS docs, and it was much, much better. And it helped me to solve the problem with hanging network interfaces in AWS as well. It was wrong configuration on our part with delete on termination and Cilium operator attribute. I've already mentioned that with AWS we have DNS load balancer, and Azure we have GCP, and at GCP we have IP-based load balancer. So we have a problem here with static versus dynamic IP addresses, because when you want to use host aliases, you need to know your IP addresses beforehand, and you need to think about collisions once, for example, your load balancer service is restarted. It can be given a different IP address. So you need to find a way to fix those addresses. Another solution is to use multi-cloud DNS. So fortunately, all those things are possible to configure in Kubernetes and all three clouds. For GCP and Azure, the configuration is pretty simple, and that's the standard configuration for load balancer IP in the service spec. However, for AWS it's more complex, and it requires AWS load balancer controller to work properly. Also, you need to think about collisions. So, for example, if you have a fixed IP address from your regular subnet, it can be taken. If you have like nodes in the subnet or any other resources that require IP addresses, you have no guarantees what IP addresses will be assigned. So if you want to grab your own IP address for load balancers, you need to have like a dedicated subnets for those fixed IP addresses or reserved pool. Depending on the cloud, you have different solutions. We've also been working on multi-cloud DNS. So basically, it is possible to configure multi-cloud resolution, DNS resolution across three clouds. Basically, you need to have forwarding zones. You need to have a specific domain names per cloud. Plus, you need to have forwarding zones in each cloud, and based on your domain name. Based on the domain name, it forwards a resolution to a corresponding cloud. With Kubernetes, you integrate your Kubernetes DNS names with cloud DNS via external DNS. And external DNS is very simple to use. That's just an extra notation to a service. We've also, first we implemented Kubernetes-only solution with core DNS. So we ran into some problems because first we wanted to have like a specific domain name per cluster, and that's possible with custom deployment of Kubernetes. However, with cloud-managed solution, it's not possible to configure a domain name per kubelet, for kubelet. So it is possible in AWS, but it's not possible in GCP and Azure. So we decided to use like core DNS and to forward per cluster domain names to localhost. So this one would be resolvable in a given cluster. And obviously forwarding zone to corresponding core DNS load balancer services with static IPs across clouds. Unfortunately, this solution has quite a big drawback. Why? Because load balancer service type can be configured only with one protocol. So you can't use UDP and TCP together for load balancer service type in Kubernetes. That's why we had to decide to use TCP only to be on the safe side. And with DNS, usually vast majority of queries is with UDP. That's much faster. What are our impressions after, or my impressions? That's my personal opinion. Does Cilium deliver on its promises? It depends. eBPF lightning fast speed, that's not in cloud. I did test comparing Cilium performance to regular cloud CNIs, and that's pretty much comparable. However, I didn't optimize Cilium, so maybe that's different. On the other hand, I noticed that in cloud mode, Cilium doesn't support some eBPF routing features. We automatically switches to legacy routing. Why? Because of the limitation of networking in the clouds. Much of networking is done by cloud itself. Load balancing and service discovery, it works, as you've seen. However, we used to have a problem. Now it should be better. We can't specify affinity for service discovery and load balancing. It would be better if you have a service implementation available in your cluster to route to this cluster. It's not that way in Cilium. At least it didn't use. In the recent version of Cilium, they've introduced some affinity configuration, and basically I think that was our request that they wanted to meet. So it's getting better there. When it comes to network policies, it's pretty good. We heavily use network policies to implement network segmentation in our network deployments. What about encryption? It works. However, our offensive security team during penetration testing noticed that encryption doesn't work on the same node. So if you have traffic inside a single node, this traffic is not encrypted. It might be not a big deal for your use case. For our use case, it was a big deal because we wanted to use Cilium encryption as our encryption in transit. But when traffic in some leg is not encrypted, it's not a solution for us, so we had to switch to MTLS across services. That's only like the top of the iceberg, because we experienced a lot of Cilium configuration knobs. We had a lot of problems with debugging networking in the clouds, and many, many more. But eventually we managed to make it working. However, ask yourself question whether or not you yourself need Cilium at all, and Cilium cluster mesh in particular. It depends on your architecture and your use case. I think that's like the case of every tool. So thank you.